Hello students, today's lesson we are going to exactly know what are measured numbers and how we are going to count significant figures. Therefore, what we are going to do today, we are going to report the measured or calculated values to the correct number of significant figures. There are two types of numbers, exact numbers and measured numbers. Exact numbers, it is either by counting. I have 2 soccer balls, 4 pizzas, whole ones. 1 foot is equal to 12 inch. 1 meter is equal to 100 centimeter. For example, I want to take the perimeter of a card. The formula for perimeter is equal to 2 times length plus width. What is 2? 2 is an exact number. It is from the formula. I don't consider it as a measurement. Therefore, exact numbers are either counting or by definition, as already I had shown you the formula. Whereas measured numbers are obtained by measuring tools. For volumetric measurements in the lab, in the chemistry lab, we have so many glasswares we use. And for example, the first one here, I have a burette. This is a 20 milliliter burette. Pipette, 100 milliliter graduated cylinder, a volumetric flask. All of this, we use them in the lab in order to take volumetric measurements. Today, I am going to show you how do we read exactly the measurement. Here I have a graduated cylinder. And I would like to notify here that graduated cylinder, I just read from down to up. Please check 2 milli. Going upward, 3 milli, 4 milli, 5 milli. In the middle, I have 2.5. I have to check exactly what is the smallest division here on this graduated cylinder. What is the smallest division? How do I read it exactly? 2, 2.1, 2.2, 2.3, 2.4, 2.5. Therefore, what's the smallest division? The smallest division is 0.1. And the uncertainty or the error of this graduated cylinder is half of the smallest division is 0.1 over 2, 0.05. Therefore here, how am I going to read my measurement? I have to read my measurement exactly at the bottom of the meniscus or at the bottom of this curve in such a way, and I have to check what is exactly now the slash that I have here. 2.5, 2.6, 2.70. Therefore, this is 2.70 and plus or minus 0.05. Why do I say 0.05 here? I told you this is the error of the tool, error of the graduated cylinder, because some of the students, they may tell you, Miss, I didn't find it 2.70 exactly. I had seen it just a little bit lower, within a range of 0.05. Here I do have another figure. In order to check exactly how do I read the graduated cylinder, I don't read too low and I don't read too high. I have to have my eye at the same level of the bottom of the meniscus. And then I read and then I take the measurement. Here I have 3 sizes of graduated cylinder. And we are going to check together exactly how much is the smallest division for each. And then whenever I check the smallest division, I read the measurement of the solution that I have in the graduated cylinder. 80, 90, in between I have 85. Therefore, what is the smallest division? 81, 82, 83, 84, 85. The smallest division is 1. And therefore, I see the bottom of the curve or the meniscus, it is 88. And what is the uncertainty here? It is half of the smallest division, which is 0.5. But therefore here it is 88 plus or minus 0.5. What about the second graduated cylinder? Here also I have to check the smallest division. 5 and 6. What are the slashes in between? 5.2, 5.4, 5.6, 5.8, 6.0. But therefore, I had seen it almost, my reading, I had seen it between 5.6 and 5.8. I had seen it in between. It is 5.7. And because the smallest division is 0.2, so therefore its half of it is 0.1. Therefore, how do I record my measurement? 5.7 plus or minus 0.1. What about the third one? As you can see that I read from down to up, as you see the arrow, upward. 5, 10, 15. This is 10, 11, 12, 13. I had seen it at 13. 13 plus or minus 0.5 because the smallest division here is 1. This is how you are going to read whatever glassware that you have it in your hand and you have subdivisions in between. You have to check the smallest division. Now I am going to explain about another glassware that we use it in the lab. This is one of the most punctured glasswares we use it in the lab. It's called burette. But here, whenever you look at the burette, it reads from up to down. 0, 1, 2, 3, and you go to 50, but it's downward. Read like and therefore from up to down. In order to check for this, in one of the examples, I have this reading, and please check with me. 18, 19, 20, 21. I'm going downward. But what is the smallest division here? 18.1, 18.2. Here I have 18.50, 19, 19.1, 19.50. And now 19.50, 0.60, 0.70. And this is 19.70, this is my measurement, in which I read the bottom of the meniscus, the bottom of the curve. This is the green measurement, that is called the correct one, in which I have my eye at the bottom of the meniscus. I don't read too high and I don't read too low. I have another example for you. Here also, and as you had seen that the smallest division is 0.1. And how do I record it? 19.70 plus or minus 0.05. Why 0.05? Because it is half of the smallest division. This is the uncertainty of the burette. But therefore I recorded 19.70 plus or minus 0.05. As I told you, there is another example for you. I'm going to read it together, me and you. 34, 35. In the middle it is what? 34.50. The smallest division is 0.1. The bottom of the meniscus is 34.60. And this is the reading and I'm looking for. It's plus or minus 0.05. This is the red here, the red reading. It's 34.60 plus or minus 0.05, which is the correct one. Okay, here I have an electronic balance in which I use it in order to measure mass. But whenever I look here at the screen of this metal balance, I can see that it has 4 decimal places, 0.0000. Therefore, whenever I want to record a measurement here using a metal balance, I have to record all the decimal places in which it's 4. For example, I have 32.1157. I don't delete any. I have to record it all, plus or minus 0.0001. This is the uncertainty of this electronic balance. For example, if my measurement, I've got it 45.5600, this balance shows me it is 5600. I don't delete it whenever I go and write it in my report. No, I have to take it as all, because already I'm using a balance in which it gives me 4 decimal places. Here I'm going to compare the precision of 2 rulers. Metric measurements. I was talking before about volumetric measurements. Now metric measurements. For example, I have a card here in which this is a red card. And I'm using a ruler in which it gives me, or I estimate, by the way, I estimate the first decimal place. I had seen that the card, it comes between 4 and 5, exactly almost in the middle. But therefore, I say to myself, it's 4.5. But this 0.5, it's an estimated value. So therefore, what do I record? The measurement, 4.5 plus or minus 0.1. Why? Because already one of the students, Miss, I didn't find it 4.5. I didn't read it as 4.5. I've seen it as 4.4 or 4.6. I tell them, yes, you're right. Therefore, it is within plus or minus 0.1. The same card, I'm going to take the measurement of this card, but using now another ruler, in which this ruler is calibrated to 1/10 of a centimeter. And now I have seen that the card, it comes between 4.5 and 4.6, almost in the middle. So therefore, what do I record? 4.55. Now I have been sure of the first decimal, 4.5, but the second decimal, I'm estimating it 4.55, plus or minus 0.01, because the same, they may tell me it is less by 0.01 or more by 0.01. Where do I read more digits? Of course, using the second ruler, I read more digits. It means I read more significant figures. Therefore, how do I record the significant figures in a measurement? There are rules. Significant figures are the digits in a measured value that are reliably known plus one uncertain digit. I have here 4.5, 4.55. The first reading, 0.5, it had been estimated, but I have to record it. In the second reading, 4.55, the second decimal, it had been estimated, but I have to record it. Okay. Significant figures are numbers which are written to reflect the percent uncertainty of a number. They indicate the precision of a measurement. The more significant figures I have, the smaller the percentage of the number is uncertain. It means it's nearer to the true value. Whereas the exact numbers, I don't record them as significant figures because they are exact. They are considered to have an infinite number of significant figures because it's not based on any uncertainty in measurement. As I told you before, perimeter is equal to 2 times length plus width. Here 2 is considered to be what? As an exact number. I don't consider it as a measurement. 1 foot is 12 inches. It's not a measurement. 1 meter is 100 centimeters. It's not a measurement. Now, let us check exactly the rules, and I have examples for each rule. How do we record significant figures? How do we count them? First rule, 1742. I have 4 significant figures. I count all digits. 395, 3 significant figures. I count all digits. The second rule, zeros between non-zero numbers are significant. Of course, here I have zeros here. I have to count it as a significant. In the first one, I have 4 significant figures. In the second one, I have 3 significant figures. But here in the third rule, I have to pay attention and I should check whatever zeros at the left, I don't consider it as significant figure. 0.002 I had it for you in red. This 0.00, it's not significant. 2, it is written in scientific notation. I'm going to explain scientific notation later in one of the videos, but here I'm just telling you how do we write it. 2 times 10 to the minus 3. This is considered to be one significant figure. The second example, zeros to the left, not significant. But here, how many significant figure I have? 2 significant. Number 4, example number 4. I have to check here at the zeros to the right. They are significant. Zeros to the left, not significant. Zeros to the right are significant. So therefore, here I have a decimal. So therefore, it's considered to be significant. 2.003 is a significant figure. 0.00 here, 0.00, 9.500. This 2 zeros, because they are at the left, I don't consider them as significant. But therefore, it's 4 significant figure. Number 5. Here, I have to check again. Zeros at the left, not significant. 420, it is written as 4.20 times 10 to the minus 3, is 3 significant. Here, let me read for you the rule. If a number is less than 1, then only the zeros that are at the end and in the middle, they are significant. To the left, not significant. The last example, I have 4 significant figures, and by this, I had summarized for you all the rules for significant. And you have to apply it according to whatever operations, mathematical operations that you do. Okay, here I have other examples for you. The first one, 6 significant figure. The second one, zeros to the left, not significant, but therefore it's 3. Here I have 5. Here I want you to pay attention for 48,000, but I have a decimal. Whenever I have a decimal, it means I have to check the zeros and to count them as significant figure. So therefore here I have them all. I count them 5 significant. 48,000, but here in this case I don't have a decimal. So therefore I consider it as 2 significant figure. 4.8 times 10 to the 4. Pay attention to this. If I have a decimal, I count the zeros. If I don't have decimal, I don't count the zeros. Here I have scientific notation. 3.982 times 10 to the 6. So I count the 4 digits, and it is 4 significant figures. And here, of course, I count the zeros in between and the zeros at the end, and I have here 6 significant figures. Thank you so much for watching me, and I hope that you understood the concept so well.